Welcome again for another video. So today this video is going to be based on conversion of NOR gate, okay, conversion of one universal gate, which is NOR gate, into the other form of logic gates. For example, we know that NOR gate, okay, NOR, okay, NOR gate basically looks like this. Okay, this is the circuit for NOR. We know that already, but we need to think of how we can convert it into one inverter first. Okay, basic gate. So just like Nand gate, the previous video, you can just go through. Okay, so you can just short the NOR gate. This is one option for converting into inverter. Similarly, you have OR gate. Okay, if you want to design OR gate with NOR, how you are going to do it? Just take NOR gate first, okay, and then just take inverter form of NOR gate. So this is our OR gate done. Next, if you want to make AND gate, okay, AND gate, this can be done just by taking inverter form of NOR first, then another inverter form of NOR. Okay, I'm not naming the variables A and B all the time, because we already know that eventually we are going to place our digital sources, okay, some inputs we are going to apply in the multisim simulation ultimately. So I'm just showing you the theory that how we can implement these basic gates in the multisim. Okay, so now I'm going to go back to the multisim software to show you that how we can design it. Okay, so NOR gate is actually 7402, this one. Okay, if we scroll, this one is your NOR gate, so you can place it one NOR gate. Okay, just select A series. So select one NOR gate for inverter, another NOR gate for OR operation, and similarly another one for the inverter form of OR gate. Next, you need inverter for AND operation. Okay, another inverter for AND operation, serially another NOR gate for AND operation. So this is how you can make your gate designing. Now we are supposed to place our inputs for sure. So just like previous videos, as I have explained, so you are going to select the sources. Okay, source number 1 for first. Okay, inverter has only one source, already. So here you will have 2 for the next, then you will have 1 and the rest. Okay, now we can add our next component, which is the indicators. Okay, so you can select indicators from here. You can select any colors, let's say red color for the first one, similarly blue color for the second one, and lastly maybe green color for the last gate. So now our next target would be to connect our components, so we can just take a wire and short for our inverter. Okay, okay, so this is how you can do your connections. So one input here, another input here, and this is how you can make your short, and then just connect, then again connect with the output probe light. Okay, so next for OR gate operation. Okay, 1 minute. So just you need to connect, that's it. you have your diagram already done, which I have shown you in the previous theory part. Okay, so now we are just implementing it, trying to design it in the simulation multisim software. Okay, so now since our gate connection is done, we can run the simulation. You can also save the file if you want, according to your name or something, and just run simulation. So since it is 0, the input, if an inverter is given 0, the output is supposed to be high. If inverter is given 1 as an input, the output, it will yield as low. Okay, so now we are trying to understand OR gate. If you remember, when you have 0 combinations for OR, the truth table, the result, according to the truth table, the result was 0. If you take 0 1 combination, it is supposed to be high. If you take 1 1 combination, also high. Let's consider 1 0 combination also, the output is high. If we consider the next gate, which is AND gate, only for 1 1 combination, okay, only for 1 1 combination, the output is supposed to be high for AND gate. If we take 1 0 combination, it is low. If we take 0 0 combination, still it's low. Let's take 1 0, okay, 1 0, still low, okay, and the rest was 0 1. Okay, you can see, you can already check for yourself. Okay, so now our basic gates are complete. We can also implement NAND gate using NOR. How you can implement NAND? Just add one inverter here. Okay, inverter logic of NAND, NOR. Okay, inverter logic of NOR. Just if you add it here. So obviously, how it is working? Obviously, due to this inverter, your input, if it was supposed to be A on this side, then after going through inverter, the result becomes A bar. If your input is B bar, let's say, okay, my mistake, 1 minute, let's say you have B, so your output would be, due to inverter, it will be B bar. So due to NOR gate, what will happen? A bar, okay, notice carefully, A bar plus B bar whole bar. This should be the output here. But when you are applying De Morgan's here, okay, when you are applying De Morgan's here, if you apply De Morgan's here, then what happens? A double bar dot B double bar. This is supposed to be after applying De Morgan's. But when you are using this inverter again, so it is becoming AB whole bar, isn't it? This double bar gets cancelled out. I have explained about this double bar situation in the previous videos multiple times. I hope you remember this. If you don't remember, you can just go through the Boolean rules, okay? Boolean rules for Boolean algebra. You can just go through those rules. There are around 12 rules, and there are 5 laws. So if we just go through those rules and laws of Boolean algebra along with the De Morgan's theorem, things will be clear to all of us. Okay, this can be a good revision before you start watching the video. It is a suggestion. If you go through those informations, then it will be better for you to understand. So this is becoming AB bar, which means ultimately NAND gate. So we can just check it here. If this operation, okay, instead of AND, if you want to make it NAND, what you're supposed to do? Just add one gate here, isn't it? Add one inverter gate. So we can easily do it. Just stop the simulation. Whenever you're doing any edit in your circuit, make sure the current simulation has to be stopped. Now you can bring one gate, okay, which is all groups. Go to all groups, select NOR gate, which has to be in inverter format. So we will just connect it. Make sure that it is shorted first, okay. Make a short connections, just closed connection, and then what we need to do, give a simulation. and you will see for 0 1 combination it is showing high because it is NAND, which means NAND is just the opposite of AND. For AND gate we had only high when we had 1 1 combination on the input side, isn't it? So you can see for 1 1 only, since it is going to invert, NAND is invert of AND, that's the reason why you are getting 1 to be inverted, which is ultimately low output. Okay, so if you take 1 0 combination, you see the result is low. 0 0 combination as well, NAND gate is working to be giving output as high output. Okay, if we take 1 0 or any combination, 1 0 0 1 combination, whatever you are taking, whenever you have one input 0 in the input side, the NAND gate is supposed to work like activated. Okay, high output it is supposed to give. So this was all about the basic gate and NAND gate as well. So after that we may proceed with the Xor exclusive gates. Okay, obviously we have seen in the previous video that NAND gate can be used to make XOR, NAND gate can be used to make XNOR. So we can do the same with our NOR gate as well. So XOR, actually, if you remember, XOR used to look like this. Okay, this was the logic symbol. So our Boolean expression, if you remember, for XOR. Okay, y, let's say y is our output, for example. Y used to be A, B, bar. Okay, A, B bar plus, 1 minute, let me write it correctly. Okay, so A, B bar plus A bar B. So this one, how you can do it using one NOR gate. You can easily take A, okay, A inverted, then you can take B inverted, and then this output can go through one NOR gate. Okay, after this NOR, this output can finally go to another another NOR gate, but before that you need to take A. Okay, let's take this one as your B and this one as A. This has to be multiplied with one NOR gate, multiplied, not multiplied actually, this has to be connected with one NOR gate. So here you have A input, another is B input. So how is this working? In order to understand that, we need to check all the steps. Here you have A bar, here you have B bar. Okay, these two are A and B, so you are getting a perfect A plus B whole bar here. Here you are getting A bar plus B bar and then whole bar. So what will happen here after passing through this particular NOR gate? It will be this, okay, plus this whole bar, isn't it? So you can simplify it if you want, or even if you don't simplify it, let's say y, okay, is our output. So we are going to get one equation here which must be similar to the given XOR gate, if it matches or not. Now we can check it. If we want to, we can check it. Okay, so A bar plus, notice carefully what I am writing. Okay, just copy pasting. Okay, A bar plus B bar whole bar, this has to be, okay, added with the second input, which means A plus B. Okay, A plus B whole bar, and then over the top, okay, over the top you will have your De Morgan. Okay, so apply De Morgan here. What will happen? This double bar, it will have one double bar, it will also have another double bar after applying the De Morgan. So it will become A bar plus B bar into multiplied. Since it is plus before De Morgan, after applying the De Morgan, it will become multiplication. Okay, A plus B. Now you can cross multiply just like the previous videos, and you can get A bar B plus. Okay, this bar is not over B, this is only over A. Okay, A bar B plus A B bar. This is what you are supposed to get along with two zeros. Why? Because A bar dot A will be one term, which will ultimately become 0, first 0, and similarly B bar dot B, if you multiply, you are also going to get 0 as well. So this is the result which ultimately matches with our expression. So now instead of wasting any other time, okay, we can just convert this into XOR gate. Okay, so let's do it fast in the simulation tool. Okay, so in order to check for the diagram, if you think that you forgot the diagram, you can see the video again, or I can show you here. Okay, 1 minute. So for diagram, okay, let me shift the diagram, or I can do one thing at least. I need to zoom in. Okay, okay, this is the diagram, so I can shift the simulation tool here. Okay, and draw the diagram here on this side. Okay, so now that we have our empty space here, so I'm going to draw it here. So we are going to use this place function. Okay, before that we need to stop the simulation first. So let's stop the simulation, place our inputs first. Okay, input number 1. Before the input, we can just place our gates. Okay, how many gates do we need? So we can check 1, 2, 3, 4, and then the last one 5, isn't it? So 1, 2, 3, 4, and then another one. Now we can add our sources. So how many sources do we need? A variable and another one which is B variable, which is enough. Okay, after the sources are being selected, we need one indicator. Let's say any colored, orange color. We may select for now. Now we need to just connect. Okay, so how we can connect it? Let's see. Here we need to short first. Okay, one short for A, another short for B. So we can connect it using the wires. Okay, next, if you see, these two outputs have gone towards the next. Okay, so this output has gone towards the next NAND gate, NOR gate, next NOR gate. Okay, and here if we see, this is connected with the next NOR gate as well. Okay, next you will collect A and B towards this particular NOR gate. Okay, so we can shift it a bit for our easy drawing if we want. Now we are going to connect using this option here. Okay, this is our A and this is our B. So after we have connected, okay, one connection was not possible previously, now it is connected. Now you can see the outputs from these two gates has gone towards the last NOR gate. Okay, so we can just connect now we don't need our diagram, so we can just connect it. After that you need to just connect with the probe. So now we can give the simulation and check whether it works like an XOR gate or not. So according to our XOR gate, if you remember, whenever our inputs were equal, our result was supposed to be low. Okay, result for the gate. If our inputs are unequal, then only it is supposed to be high. Okay, 0 1 unequal input, so the NOR NOR actually it is XOR. Okay, unequal inputs, so XOR. If equal inputs, then XOR gate is showing low. Okay, let's see another unequal input, which is 1 0, so it is showing high. If we take another equal input, for unequal inputs only, the XOR gate is supposed to show high output. So this was all about our XOR gate. Now we can proceed with our XNOR. So how you can make XNOR gate? Obviously by introducing one inverter. So this is one home task to you. I hope all of you can do it. So thank you very much for today's video. I hope you will practice at home.